Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 2 part of this playlist, which is discrete random variables, and today's topic is a negative binomial distribution. First, quick development and intuition. Assume we have an infinite sequence of Bernoulli trials with parameter p. How many trials are needed to observe exactly r successes? This is what a negative binomial distribution models. Now, when r is equal to 1, this is a geometric distribution, which we covered earlier in this playlist. So let x be a negative binomial random variable. The density of x is f of x, which is this. Now, I'm going to give you a little intuition. First of all, x goes from r plus 1, to etc. We have to observe r trials to see r successes. Could be more. But if the last trial is a success, that means the previous x minus 1 trials, there were r minus 1 successes. And they can be mixed in there anywhere, right? We don't know. So the number of successes, the probability of r successes is p to the r. The number of x minus r failures is 1 minus p raised to the x minus r. But we have to account for how many ways we could mix up those first r minus 1 successes. And that's x minus 1 choose r minus 1. It's combinations. And that's the density. Now, some call it a probability mass function. That's fine. This is a density of the discrete type. So it's okay to say it that way. R goes from 1, 2, 3, to whatever number we want. Let x be a negative binomial random variable with parameters p and r. The moment generating function of x is given by this expression. Now let's prove it. Let x equal x1, x2 to xr, where xi are independent geometric random variables. And first let's explain what's going on there. x1 is a geometric random variable, so it's how many trials until we get to the first success. And then x2 is, we go how many trials to the first success. We do that r times. So and we add them up. That's how many trials to the rth success. So these are equivalent. And we're going to use theorem 6 from video ims20. And that's the 15th video in the playlist Introduction to Mathematical Statistics. Happens to be the moment generating function video. So m of t is the expected value of e to the tx, but since x is the sum of independent random variables, it's the product of their moment generating functions. And the moment generating function of a geometric distribution was this expression here. We're taking the product r times. That's why it's raised to the rth, and that's what we wanted to show. Now, let x be a negative binomial random variable with parameters p and r. The mean of x is given by r divided by p. So first proof, let's use the moment generating function to derive the first moment. So this is it. We take the first derivative of x and you get something like this, or at least that's what I did when I took the first derivative. Then there were a few more steps and it simplified to this. Now we evaluated it t equals 0, right? The expected value, let me rephrase that. The first moment of x, which is the expected value, is the derivative of the moment generating function evaluated t equals 0. So you plug in t equals 0 here and you get this expression. 1 minus q is p. We get a lot of cancellations, r over p, and that's what we wanted to show. Now, a second proof is if we let x equal the sum of these r independent geometric random variables, then the expected value of x is the expected value of the sum of these independent geometric random variables. And then it's the sum of the variables, and each one is a geometric distribution. And so its expected value is 1 over p, but there's r of them, so it's r over p, and that's what we wanted to show. Let x be a negative random variable, a negative binomial random variable with parameters p and r. The variance of x is given by rq over p squared. Now, again, you could use the moment generated function to do this, but it's quicker and easier if we use this approach. Let x equal the sum of these r independent geometric random variables. Then the variance of x is the variance of the sum, which is the sum of the variances because they're independent. The variance of a geometric random variable is q over p squared. We're adding them up r times, so it's r times that number. Let's do a simulation of flipping a coin until the rth head. So we're going to create a function. Its parameters are, which you have to input, and we're going to count the number of rolls it takes to observe the rth head. So our head count, so that's when we flip a coin, it's either a head or a tail, and so we're going to add them up as we go. So the result is continue until we get to the rth head. So we're going to flip a head. So head count, previous head count. We're going to add a 0 or 1. It's a 1 with probability 1/2. That a 1 is going to represent a head. And if the head count is r, we stop. Otherwise, we continue. So we add a roll number. We roll again, add it to the previous head count. Stop if head counts r. Otherwise, we continue. Oh, and I don't know why I don't make this bigger each time. I always tell myself I'm going to, and then I don't. So here's the function that we just looked at. And now let's run it. Let's put in 4. So this is going to tell us how many flips it takes to get 4 heads. Oh, and it took 4, which is kind of unusual. We flipped a head 4 times. We're going to flip a coin till we see the 10th head. It took us 31 times. Well, let's do a simulation of that, of 700,000. We're going to use sapply, and we're going to flip a coin. We're going to see how many flips it takes to see 4 heads. And then we're going to do that 700,000 times. We're going to store the results in flips. So flips is a vector of length 700,000. And it's actually the number of times it takes to observe 4 heads. And each component is independent of each other. So the mean number of flips is 8. And if you were to go back and plug in the numbers to the mean that we derived, that's exactly what it is. Variance of flips is 7.98. I think it should be 8 exactly, theoretically. But let's create, now that we have a vector of all the time, the number of times it takes to get 4 heads, let's look at the distribution of those. So let's create a bar plot with the flips. And that's what this is. So this is the gray bars are the probability in our simulation. So these are the simulated probabilities of it taking 7 times to observe 4 heads. Here's the probability that it took 17 times to observe 4 heads. Gray is simulated. R is the exact calculation. So we put in the formula exactly, and boom, and it prints it. And notice that they're very close. Of course, if you're going to simulate something 700,000 times, it's going to be really close to the theoretical. Okay, well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.